All right, welcome to our video lecture for section 2.5. This is the first couple warm-up problems, and I wanted to start by just showing you the answers for the first question A and B, just so you know what I'm looking for with questions in this form. So when I say for each graph, starting with the warm-up 1 graph of f of x, on what intervals is f prime of x positive means what are the values of x that make it so the derivative is a positive number there. And you can see here the whole graph, it looks like the slope would be positive because it's increasing from left to right everywhere. So on what interval is that? That's negative infinity to infinity. You could just write that also as all real numbers. That's where the derivative is positive. And on what interval is f prime of x negative? That's nowhere, because if f prime of x were negative, it would be slanted downward somewhere. So there's no values of x. So you just say nowhere or no values of x or anything like that. So I'll let you try the rest of these. Oh, and I meant to warn you that part C and D are hard. If you get confused by that, give it a shot. Don't bang your head against the wall though, because I'll explain it all when the answers appear after you pause it. So pause it now and try it out, because the answers will appear in 3, 2, 1. So for number 1 here, like we said before, it's increasing everywhere, decreasing nowhere. Is f prime of x increasing or decreasing here? Well, what I would say is here, f prime of x would be a big positive number, and then as x increases, the graph gets less steep. It's sort of curving downward a little bit. So you start out with big positive slopes, but then they get closer to 0. So that actually means f prime of x is decreasing. So that's why it's decreasing everywhere instead of nowhere, and increasing nowhere. So in fact, if we were going to draw the graph of the derivative of this, I would say it looks something like something sort of like that, or maybe that's more precise. I don't know. Yeah, it looks like it is the derivative is always positive here because the function is always increasing, but because the original function is increasing at a slower and slower rate, that means the rate of change is going down, getting sort of closer to 0. Okay, so with number 2 here, the original function is increasing on this side, so that means that f prime is positive from 2 to infinity. And you notice I didn't, this is a round parentheses here, although it's a little funny looking. That round parentheses means that you're not including 2 in this interval, because remember, f prime of 2 is actually 0. So even though f of x is increasing from 2 to infinity, f prime of 2 is equal to 0, so that 0 is not positive. So that's why this interval shouldn't include 2. And so there are weird discrepancies that come up like that in calculus, where it's not exactly the same thing for f prime to be positive and the function to be increasing, because sometimes f prime would be 0 and you can still have an increasing function there. We'll look at some more examples of that. Anyways, f prime of x is negative, where this is decreasing, except when you get to f prime of 2. Again, f prime of 2 is 0, so you don't include that in this interval. Then f prime of x is actually increasing everywhere and never decreasing. Why? Well, let's look at what would happen if we drew a graph of f prime of x here. Well, we know that f prime of 2 is 0, so the graph of f prime has to have that point. Then to the right of that, f prime is positive and getting to be bigger and bigger positive slopes here on the graph of f, so it would go up something like that. I don't know. And then on the left, over here you have big negative slopes, and then the slopes get closer and closer to being flat, and that means you start with a big negative derivative, and the derivative gets closer to being 0 there. So yeah, so it looks like this, it might not be exactly a line, it might be some weird thing, but it is going up to the up from left to right. So that means f prime of x is actually increasing everywhere, and it's never decreasing. And what this section is going to be about is actually what does the shape of the original graph have to do with the derivative of the derivative. So now we know a derivative is its own function, because you can just graph every single point, and then you could look at the tangent lines to the derivative function, and what is the slope of that? That's that function that you get is called the second derivative, and we'll look at that in a moment. All right, so here is just the official definition of f prime prime is the way you read that, or you can just say the second derivative of f. It's the same as the limit of a difference quotient as before. It's just instead of plugging in values of f, you're plugging in values of the derivative. So what this gets you is when you do the limit of the change in the derivative divided by a corresponding change in x, what you get is essentially the slope of f prime of x at that value of x that you're plugging in. So we write this sometimes with Leibniz notation, like so. So remember, Leibniz notation for the derivative is just dy over dx, and you can think of that as the same as just multiplying d over dx times y, and if basically d over dx is we use it as a symbol that means like take the derivative of something with respect to x as the variable. So it means take the derivative of y with respect to x, or you could also write it this way. We do the same thing with the second derivative. You write take the derivative of something with x as the variable. That it would look just like this here, but what we're taking the derivative of is already the derivative, dy over dx. So if you just sort of think of the d as like a variable, and you do d times d, you can call that d squared. And then if you do dx times dx, call that dx squared, which is a little weird because remember, the d isn't really a number, so we're not actually like multiplying a d times another d, but it's just a way of shortening this notation to say we're doing the derivative of dy over dx. Anyways, let's look at the relationship between the second derivative and the original graph f of x. But first, just remember some rules from before. If f prime of x is greater than 0 on an interval, then that means f of x is increasing there. And if f prime of x is negative on an interval, that means f of x had negative slope at that point and is decreasing there. So I want to just look at that statement, but then instead of talking about the same relationship here between f prime and f, well, f prime prime is actually the derivative of f prime. So I'm just going to take the statement whoops, except I wanted to copy it. Okay. So saying exactly the same thing, but talking about the second derivative, if f prime prime of x whoops, f double prime of x, which is the derivative of f prime of x, that means if f double prime is greater than 0, then that's a derivative of f prime, so that means that f prime is increasing there. And what does that say about the actual graph of f? That's going to mean that if f prime is increasing, that means the slope is like getting more and more steeply positive. That goes along with being concave up, and we'll look at an example of why that is in a second. So the original graph f is concave up, which, remember, concave up means it could be shaped like that, or like a parabola or something, or maybe like something like that. All of these have the curved shape. The curved part is upward. So and if f prime is decreasing, that means f of x is concave down, and concave down means the graph might look like that. That's a concave up, because our concave down, an increasing function, or it might look like that, or it might look like just this part. So these are three concave down functions, and to see why that is, why does f prime of x increasing make f of x concave up, and why does f prime of x decreasing make f of x concave down? I wanted to show you an example of how that might work. So here is our an original function. F of x is just this parabola here, downward parabola here, and I wanted to see what happens to the derivative, and the derivative at a point in the middle here, like if I plugged in 0.5 or so, the slope of the tangent line at that point would be about 1.3, because that tangent line through the point would be about the same slope as the secant line. So that slope there is about 1.3, but if you start from the left here and see what happens to the slope here, you have a big positive slope. If you plugged in like -1 over here, or -1.5, you have a big positive slope, about 3, and then the slope becomes smaller and smaller positive numbers. It's still increasing, the function is still increasing, but the slopes are getting less steep. And then there's a moment there where the slope is 0, and then as you go further to the right, the slope becomes bigger and bigger negative numbers. So you can imagine that if you were going to draw a graph of this derivative of this, which we can do here. If we're going to, let's try to draw the derivative of this. Well, let's see. It would end up looking something like, well, we have a big positive slope over here, so we said the derivative was about 3 over here. Whoops. So the derivative was about 3 over here, and then the slope became less and less until we got to this point where the slope is 0, and then over here the slope is bigger and bigger negative numbers, which means you continue decreasing, getting lesser and lesser slopes that way. So f prime looks something like this if your f of x looks like that. And that's just an explanation for why if f prime is decreasing, then f of x is concave down, something like this. And I just want to expand on that a little bit more. I just moved this around so you could see it all in one screen here, but also talk about the converse of that. So what we have here, these first things we're talking about, this is an if-then sort of statement. If something is true, then this other thing is true. The converse is like, what if you start by saying, if it's concave up, can you conclude that f prime of x is actually positive there? And it turns out the answer is not exactly. So if you know that f of x is concave up, and you know that f prime of x is defined there, and that's important because sometimes double prime, excuse me, f double prime of x might be undefined. But anyways, if it is defined, then it will be greater or equal to 0. And if f of x is concave down on the interval, and if f double prime of x is defined there, then f double prime, the second derivative, will be less than or equal to 0. And it's a little finicky, this stuff, because like, why is this less than or equal to 0, and why is this one less than 0? And the answer is there's just a lot of weird kinds of functions out there that break one of these rules and not the other. One example of a weird function like that is this one. It's not even that weird of a function, but if your f of x function is just x to the fourth, it turns out that, I mean, if you just make a graph of this, it looks like a parabola that just gets a little bit flatter than a regular parabola does near the origin, but it still has the same sort of basic form of a parabola. Now, it turns out the derivative of this function, so this is, let me just graph, this is f here. The derivative of this function turns out to look kind of like this, where it flattens out so much near 0, 0, the original f of x does, that the derivative itself flattens out, even though it goes up like that. So the derivative would have that kind of shape, and then the second derivative, when we graph that, is going to look like a parabola there, and it will actually touch the origin. So this is an example where f of x is decreasing, or sorry, I shouldn't say decreasing, it's concave up. And f prime of x is decreasing, sorry, increasing, whoops, everywhere. So f prime of x is increasing everywhere, but because f prime is flat, has a horizontal tangent line here, that means that the second derivative at 0 is actually equal to 0, because the slope of the tangent line there, if you're going to draw the tangent line to f prime, would be 0. So that's why you can't conclude that f double prime of x is always greater than 0, because it might be equal to 0, but at least it's greater or equal to 0. So there's weird functions like that. Let's look at a couple more examples. Here's a couple examples to try. First of all, here's a linear function. Draw a rough sketch, doesn't have to be pretty or exact or anything, of what f prime of x looks like here and what f double prime of x looks like here. And then for part B, you have a function like this. I didn't make it very smooth, but it has this shape. Draw its derivative and second derivative. It doesn't have to be perfect. And then for example 2, suppose we have a car's position function. Interpret both of these facts. S double prime of 10 is -5 meters per second per second. If that's confusing, don't bang your head against the wall. But let's pause it and give these a shot, and the answers will appear in 3, 2, 1. And here are these answers. So with example 1a here, the slope is positive here, and it's always exactly the same at every point, so the derivative of it should be a constant function where the value of the derivative is always equal to the same y-coordinate here. And then when that's always flat here, then that means it has 0 slope. So f double prime is the slope of f prime, which is always 0, so this function is just always 0. And that kind of makes sense if you think about the second derivative as representing concavity. And concave up means the second derivative is positive. Concave down pretty much goes with the second derivative being negative. But this is neither concave up nor concave down. You could say this has no concavity. It's not curved at all. So that shows up here. If it's 0, it's neither positive nor negative, because 0 is neither of those. So that's always true with linear functions. They always have no concavity and 0 as a second derivative. For part B here, this has negative slope out here, steeply negative slope, so a big negative number is f prime of x. Then the slope gets closer to 0, it gets flatter and flatter, so f prime of x, the y coordinates here, get closer to 0, but still they're always negative. Then this one, now f prime of x itself is increasing here, because going from originally having negative slope to closer to 0 slope means f prime is an increasing function itself, and it always has positively sloped tangent lines. So that's why f double prime is always positive. And that goes, so this is always positive, that goes along with this being concave up originally. Okay, and for example 2, s prime of 10 is equal to 20 meters per second. Hopefully you said that means after 10 seconds the car is going 20 meters per second. But the weird thing is, what does s double prime of 10 mean? Well, this gives you the rate of change of s prime. You can think of this number as is the rate that velocity is changing and the rate that velocity is changing is also called acceleration, is what you can think of this number. And this is negative, so velocity is changing at a negative rate. That means the car is slowing down. So it's slowing down at a rate of negative 5 meters per second and that's pretty ugly units. Having like fractions within fractions is awkward in your units. So that's why if you think about just multiplying both sides of this by seconds, multiply the top by seconds, multiply the bottom by seconds, that's why this is the same thing as negative 5 meters after the seconds cancel out, divided by seconds times seconds, which is seconds squared. So seconds squared, you can't really picture what a square second is, but that's just a way of writing meters per second. And let's talk about velocity and acceleration for a little bit here. So if we're just generally giving some position function, y equals s of t, we talked about velocity before, is the derivative of this, which you write as either dy, change in position, over a small change in time, and you can write that as s prime of t, and you could also just write that as the v of t function, which we'll use this notation v for velocity a lot. So that's that. Now, if we look at the rate of change of this, how is this function, velocity, changing as time changes? That's just called acceleration. And you can write that as d squared y over dt. You could also, or over dt squared. You could also just write that as d, or you could write it as v prime of t. And v itself is s of t, so you can write that as s double prime of t if you want, and you could also just write it as a of t. That's the acceleration function. These are all different notations for saying the same thing. Hope it doesn't get too confusing, but if you understand what the symbols mean, it hopefully makes some sense. And let's look at, I think, one more example and then a couple practice problems. Here's another example we're going to look at. This one, I'm just going to sort of talk about it. You don't need to really do it yourself here. I just want to see how we can relate the graph of a function to what it says about the real life situation. So this is the kind of thing that shows up a lot in biology, where there's some kind of population of some kind of organisms. It might be some bacteria in a petri dish, or it might be some rabbits that somebody let out onto an island, and then their population grows. And this kind of graph, the kind of function you use to model this kind of thing is called a logistic growth curve. And what I want to look at is P is the population here, T is time. What is the second derivative of this, say, about the rate of growth and the changes in the population, and what are the practical interpretations of T0 and L? So first of all, let's see, what do we know about d squared, or sorry, just dp over dt? dp over dt here, is that going to be positive or negative? Well, it looks like the original function here is increasing, so this will always be positive everywhere. But it's not exactly increasing everywhere. It looks like it starts off kind of slower, and then it's increasing faster and faster here until you get to this point where it looks like the slope here is the steepest. Now, this is a thing that happens in real life. If you imagine that you start by putting 10 bacteria in a petri dish, so maybe this is starting at 10, then it takes a certain amount of time to get up to 20. Then when there's 20 bacteria in there and there's plenty of food, then they're going to be able to grow. They're going to be able to grow faster because there's more of them to eat. So then they take the same amount of time to reproduce, and they get up to 40. It doesn't look exactly like that, but they get up to 40 pretty quick here. My drawing isn't very good, but the point is that when there's more bacteria, they can reproduce faster because there's more of them. So like first they'll double, and then they'll double again, and then they'll double again in the same amount of time. But then at some point they start running out of food, or maybe there starts to be more predators that can start eating them when there's more of them, if you're talking about rabbits on an island. And the rate of growth kind of flattens out here. So dp over dt, the rate of change of this is increasing on the interval 0 up to t0. And that means when that happens, what is the second derivative doing? The derivative of dp over dt. If dp over dt is increasing because it's getting steeper, then that makes this positive. And then t0 is the point where it's increasing the steepest, and then after that the rate of change flattens out. So we can say that dp over dt is decreasing on the interval from t0 to infinity, it looks like here. And that means d squared of p over dt squared is negative. And So what are the practical interpretations of t0? Well, t0 is the place where the derivative is at its maximum, where the population is increasing as fast as possible, and then it starts running into problems with running out of resources or whatever the limiting factor is. So I'll just say t0 is the point of maximum rate of change of p with respect to the time. And what is L? L is like the maximum capacity of the confined environment. It's how many it can hold without them running out of food or getting eaten by predators. So I think you call that the carrying capacity or something in biology. I'll just call it capacity. Of the confined environment that they're in. And after this, we'll do a couple of practice problems. Okay, here's a couple practice problems. The first one has this table which shows you the velocity of a sports car. So for example, after 6 seconds, the velocity is 42 meters per second. After 9 seconds, the velocity is 59 meters per second. And if a of t is the derivative of this function, is this acceleration, the derivative of velocity, is that positive or negative, and is it increasing or decreasing? And for problem number 2, we're going to draw two functions. Draw one function of a graph of y equals f of x, where f prime is negative everywhere, but also f prime is increasing. So a function whose derivative is negative but increasing, and then another function g, draw that so g prime is positive but decreasing. And let's pause it now and do these problems, and the answers will appear in 3, 2, 1. Here's the answers to these. So for this first one, if this is velocity, then the derivative of that we can approximate by getting average rates of change between the two things. So over the first 3 seconds, the velocity goes from 0 to 23. So that's an average rate of change of 23 meters per second in 3 seconds. And then it goes up by 19 in 3 seconds, and then it goes up by 17 meters per second in 3 seconds, and then by 13 meters per second in 3 seconds. And those are all positive numbers, right? The car is speeding up. You get higher and higher velocities. So this turns out that A of t is positive everywhere, but then you also notice that these are smaller positive numbers. So it is still speeding up, but the acceleration itself is getting smaller. So A of t is decreasing. And by the way, this means that A prime of t is actually a function called the jerk for some reason. The jerk is the rate of change of acceleration, and that is negative here. Because the acceleration itself is decreasing. So the position of this car is probably always positive. The velocity is definitely always positive. The acceleration is always positive. And but it is accelerating at the rate of change of acceleration is itself negative, which is weird. Anyways, for problem 2 here, let's draw a function where f prime of x is less than 0. That's this one. We have negative slope at all points, but f prime of x is also increasing. So this one has f prime less than 0, but because f prime is increasing, f double prime is greater than 0. And then this second one here, this is g of x. Whoops. So g prime here is positive because the function is increasing, but it's increasing at a slower and slower rate. So the rate of change of the rate of change, or the second derivative, is actually negative. So just wanted to go over some weird things like that. Some tips for this section. I should say, when you're talking about this and when you're doing homework, it's important to try to be clear about what function you're talking about. I probably messed this up myself a couple times in this video, but if you use the word it to talk about a function, like if you say it is decreasing, or it is increasing, or it is concave up or concave down, or it's positive or negative, you don't know what function you're talking about. So don't say it, say either, be clear about which one you're talking about. You either say f is positive or negative, or f prime, or f double prime, and that way when you say f prime is positive, you're not saying f is positive, you're not saying f double prime is positive. So you don't say it's positive, you say f prime is positive, or you just be clear about what you're saying, or it will get really confusing really fast, is what I'm saying. But it is a fun section to explore, so I'll see you in class and we'll try some more stuff like this.